All right, folks. Y'all had a good weekend? Good Labor Day weekend? Yeah. I'm gonna hand back your exams at the end of class. I posted the solutions yesterday. I sent an email out about it, so that'll be important for you to have because the final will be cumulative, and I'll take the final largely from those old exams. You see. Uh, so those you'll want to study those old tests for your final. I'll take those questions. I'll sort of change them up a little bit, but it'll be largely your exams for the final. Not all of your exams, but I'll take them from the exams. Okay? You feel okay about that test? I know some of you feel good. I know some of you don't feel so good. And that's okay. I want to show you something just sort of give you a little perspective about what you might have made on that test and just let you realize and understand that we have a long ways to go and a lot of opportunities to do better. So on the website, you have this grade calculator, and you can go on there and you can put in sort of, hey Janae, you can play around with the numbers that you have. So let me zoom in here first. I think I've shown y'all this before. This is just sort of everything that we've had. So here, these are the maximum points that you can get for the various things. This is what we've done already, that first exam. Notice that this only counts for 16 or 17% of your grade. That means if you made a 0 on this exam, the highest grade that you could get would be an 83%. So that's all right, right? I could live with an 83%. That's if you get a 0 on this exam. If you got a 50% on this exam, then the highest grade you can get is what, like a 92, right? You can live with a 92, right? That just means you have to get perfect scores here on out, which you can do. Everybody can do. Um, I would like to get to the end of the class. I'd love to have no Fs this semester. I'd really love to have no Ds because if you make a D in this course, you know what's going to happen? I'm gonna see you again. I like you a lot, right? But I don't want to see you again. So I know that some of you didn't do so well, and that's okay on the first exam, but hopefully you got a good feel for how to prepare for the exams. And when you get your exam back, you can take a look and see where you lost points. Some of you lost a lot of points on the free response. Some of you lost a lot on the multiple choice. So you can sort of see where you were in that and see how to prepare. I'm here to help you. That's my job, right? To help you do well in the course. So you can come see me. I can help you prepare. They also have good tutors over in the tutoring center that can help you as well. If you're not familiar with the tutoring center, it's a really good deal for students. It's like 25 bucks, I think, for the semester, but then you cover all courses. So I know a lot of you in organic, I think. They have organic tutors. Is that true? They have an organic tutor over there? They should have an organic. I'm pretty. Oh, it's per course now. It's still a darn good deal, all right? Because tutors are usually 25 bucks an hour, not for the whole semester, and they have some good tutors over there. But again, for this course, I can be your tutor too. So even if you want to set up a weekly time, I'll do whatever needs to be done to get you out of here without a D or an F. I really don't like D's or F's at all. Okay? Y'all don't like them either, do you? But overall, the exam was pretty good. I thought students did well. The class as a whole did well. Um, Anyway, so you can play around with this. You can put in your grades here and see how it affects your final average. Sort of estimate what you think you might make on the other the other three exams, and the final. I did put class participation up. I fully expect that if you come to class regularly, you might miss a few times or whatever, that you'll max out that class participation. In between the third and fourth exams is when students will start maxing that out and getting it up to the full 50 points. Usually at the end of the semester, I might have 3 or 4 students that don't max that out, and those are just students that I didn't really see very much. So uh, you should be right around, I think I said the max for that class participation was 13 or something. Is that what I said? Yeah, you should be right around 10 points. If you're a little below that, don't sweat it too much. Just make sure you're coming to class. You have any questions about what that number meant? I think I might have still had one student who wasn't registered. So if you had 0 points for that, make sure that you send me your clicker ID or come see me afterwards. We'll get you set up. It's not that you have 0 points. It's just that I don't have your clicker registered. I also did put in your clicker ID, so if you just want to check that, it's under feedback for clicker ID, I think I did for your class. You can just check your clicker and make sure that it has the right ID. I'm pretty sure I have everybody correct. Have any questions about the exam or sort of what's coming up? we're moving into chapters 3 and 4, and we might even get a little bit of chapter 5 on this next exam. Chapter 3 will be vectors, which is really just trig, and then we'll do two-dimensional motion, which is really just chapter 2 with a little bit of trig thrown in, and then we'll start doing force vectors, which if some of y'all are in Calc 3, y'all have done this already, a lot of what we've done with vectors, like force diagrams and stuff. Okay, okay, yeah, we'll get to that soon. Chapter 6, I think. Anyway, let's continue on with vectors. Uh, we've seen this a little bit already. You want to watch the Bob the Builder video? It's a good way to start a Monday morning, or a pseudo Monday morning, Wednesday morning. Let me pause. All right, so the point of that is that if I think about displacement, for example, displacement, I have an initial position and I have a final position. And as the crow flies, a bird would go in that direction, but realize that it's going to be the same, and we'll see this when we start doing sums of vectors, that if I take another route, that this displacement is equivalent, that the red vectors all added up are equivalent to the blue vector. All right, so just a little bit about vectors. We've already seen this some, but vectors have magnitude and direction. And scalar quantities have a magnitude only. We usually draw vectors with an arrow. So for example, if I'm talking about displacement, I'll draw it with an arrow like that. Or say a force, I'll draw it with an arrow, or velocity. All these are vector quantities. So I usually put an arrow over the top of it. Sometimes we'll use a caret or a little hat on the top of it. So for example, when we're talking about our unit vectors, I'll do I, J, and K. And we'll see those a little bit more later as we go along. Those are just the vectors that represent the X, Y, and Z axes. They're still vectors. They have a magnitude of 1, always a magnitude of 1. We represent a vector graphically just as an arrow. Right? Now this arrow has a length, and the length of the arrow gives the magnitude. So whatever the arrow's length is, that gives the magnitude. In the lab, some of y'all have already had the lab, but if you have the lab this week, you'll do an exercise where you do graphical sums of vectors, and you have to draw the vectors to the appropriate length. So you have a certain scale, you say like a centimeter is 1 Newton, and then a 5 Newton vector would have a 5 centimeter long arrow. So the length of the arrow gives the magnitude, while the direction is the direction. So the direction is the direction of the vector is the direction of the arrow. So often we'll talk about the direction of this arrow as an angle. So for example, I would say an angle theta above the x-axis. Um, for example, if I have a vector, I can draw different lengths. So I draw one vector like that and one vector like that. The smaller vector in this figure has the same direction, but half the magnitude of the larger one. Just because I drew it half the length. All right. So if I have a vector, the length of the vector represents the magnitude. Did it go down? Two vectors are equal if their magnitude and direction are the same. You can draw them in different coordinate systems, or you can translate them over. So if I have a vector like this, that vector is equivalent to this vector, it's equivalent to this vector, it's equivalent to that vector. All those are equivalent. I can move them around as long as I don't change the length of the vector, or I change the orientation or the direction. So these are all the same as long as you don't change their magnitude or direction. we're going to look at the graphical or the geometric or the graphical method of adding vectors. It's called the tail to tip, it's sometimes called the triangular method. It's very similar to the parallelogram method of adding vectors. So you might also see it called the parallelogram. On the next test, you'll have some multiple choice questions where I ask you to do graphical addition of vectors. I might also ask you if have you add up of sum of vectors to sketch out the vectors, and that's what I'm doing here is just the geometrically or graphically adding up the vectors. So let's say that we have two vectors, A and B. Let's say that vector A looks like this, and vector B looks like this. I can find the sum of the vectors by placing the vectors tip to tail. I call it the tail to tip or the tail to tip rather. And then connecting the tail of A to the tip of B. Here I'm calling this the tail and this the tip. So the tail is like the back end of the vector, and then the tip is the front end of the vector. So if I want to know the sum of A plus B, all I do is I draw the vector A like this, and then I draw the vector B like this. Remember, I can translate them around however I want. And then the sum of those will be the vector A plus B. I draw the first vector first. I draw the second vector second. I draw the tail of the second vector to the tip of the first vector, tail to tip. And then I start at the tail, and then I go to the tip. I start at the beginning part, and I go to the final position. I always think of this in terms of displacement, though it holds for all vectors. Like Spud, when he goes to Bob's shop or whatever it is, he travels along which of these paths? The A plus B or the A and then the vector B? Right, he goes as the crow flies along A plus B, right, the straight line. But that's equivalent to this path if I go along vector A and then I go along vector B. So these two are equivalent. That is to say that A plus B is equal to A plus B. So the vector A plus the vector B is equal to the sum of those A plus B. That should be fairly obvious, I think. Is that obvious? Yeah. This is, gosh, what's that property? I'm never going to ask you the properties of vectors, but I think it's commutative. Is that right? Where A plus B is equal to B plus A. Is that the commutative property? I think it is. Don't tell anybody I said that, but I think it is. So it's also true that A plus B is equal to B plus A. And we could represent that graphically by first drawing B and then drawing A. And then notice that this is the same vector. Right, that gives me the same result because vectors are commutative. You can switch them around. A plus B is equal to B plus A. If you are subtracting vectors, you simply switch the direction of the vector that is negative. So let's say, for example, this is my vector A. This is my vector B. If I want to know what is A minus B, I'm going to draw the vector A. Let me redraw that actually. Sorry, some more space. Draw the vector A right here. And then I'm going to draw the vector negative B. And the vector negative B is going to look like this. All right, all I did was I took this vector B and I just flipped it 180 degrees. I just switched the ends around. So that's the vector negative B, and then the sum of those two vectors, starting at A, starting at the first vector, going to the end of the second vector, that's going to be the vector A minus B like that. Okay? So that's how I take the difference of two vectors, A and B. I can also do this for more than two vectors. I mean, you can do it for billions of vectors if you want, and people do that. Uh, if I want to add up more than two vectors, I just do the same thing. I just draw the first vector, I draw the second vector, draw the third vector, draw the fourth vector, and then the combination of all those will give me the sum. So if this was vectors A, B, C, and D, then the blue line would represent the sum. All right, let's think sort of a little bit about vectors. Let's say that I have two vectors that are 12 and 8 units. A is 12 units long, B is 8 units long. If A plus B is equal to R, what are which of these rather is an appropriate answer? I'm going to give you four options, and then you can click in. Which of these would be a potential answer for these? We'll just say that 2 units. All right. If I'm going to add up vectors A and B, and I know that their magnitudes are 12 and 8 units, which of these is a possible solution to adding up those vectors? Is it going to be 2 units, 6 units, 21 units, or 96 units? There's only one possible answer here, so I want to pick out which is the possible answer. Think about what are the maximum and minimum values for that sum A and B. I'm going to stop in about 10 seconds. We just missing a lot of people? I'll stop at 1 minute. Okay, C is not right. It's going to be B. How could you possibly get 21 units? Now remember, there's a maximum and a minimum. What is the maximum for vectors 12 and 8 units long? What's the maximum sum that you can get? It's going to be 20. And that's if they're in the same direction. So my maximum value is where I have one vector that's 12 units long here, and then another vector that's 8 units long, and then the sum of those two vectors would be 20 units long. And then what's the minimum value that I can get for this? 4. Yeah, so I can have 12 in this direction, and then I can have 8 in this direction, and that means that the sum of those two vectors is going to be 4 units long. You follow me on this? All right, so the difference are the solution has to be somewhere between 20 units and 4 units, so it's going to be 6 units. We'll see another question like that in a bit. Let's try this question. Let's say I have two vectors, A and B. What is the result of the difference, A minus B? So looking here for the difference, A minus B, which of these arrows represents that? In case you can't see this, this is A, B, C, and D. Which of these represents A minus B? I'm going to stop at 45, 45, 45. All right, let's see. A lot of you put A, and a lot of you put D. Ah, yeah, so A is not correct. Let me show you why, but it's a very common mistake that people make. D is the right answer. The way that you got A, which is the incorrect way, is that you drew the vector A, this is A, and then you drew the vector negative B. You drew negative B correctly, right? But you didn't place the vectors in the proper positions. And then you said, well, this must be the answer, right? That's not correct, but students often do that. The correct way to do it is you draw the vector A, and then you draw the vector negative B. So this is A, this is negative B, and then you start at the beginning of A, and you draw it like that. So D is the right answer. That matches up. Remember, I always think about displacement whenever I'm thinking about these. The arrows show the direction of my path, and so I go along this arrow, and then I pick up, and I go along this arrow, and I get to this final position, and I say, aha, that's the same as starting here and going in this direction. I always think of displacement, but also it holds for all vectors. It holds for force vectors or um, velocity acceleration. I would expect to see at least a multiple choice question like that, but also if I give you a set of vectors and ask you to add them numerically, I might ask you to sketch them out as well. It always helps to sketch out vectors. Oh, let's see, let's try this. This is very similar to one we just did, so should be pretty straightforward. Which of these is a possible solution for the sum of A plus B? I'm going to stop at 35. 35, just guess if you don't know. Okay, good. C is the right answer. The minimum is 13. The maximum is 37. So 32 is the only one that fits between 13 and 37. All right. I'm going to go through the components and how to add vectors. But you know what? This is really just trig. This is something that we've already had. Remember your trig definitions, that SOHCAHTOA, and then also remember your Pythagorean theorem. You'll need to know that for the next several chapters because we'll have vectors in all those chapters. In fact, we'll see vectors until the end of next semester. So you'll be dealing with vectors a lot, but fortunately it's not that difficult. Like there are only a few little things that you need to get, but then you'll use those things over and over again. So if you get them now, good for you, and you'll do a lot better in the coming days. So first of all, we need to realize that a vector is made up of components. The component is like a projection onto the x or y axis. I like to think of it as like a shadow. So if you imagine like a flashlight and it shines light onto this vector and it casts a shadow onto the y-axis. So if I imagine casting this shadow onto the y-axis, I'll get this projection of that vector onto the y-axis. And similarly, I can cast a shadow onto the x-axis and I get a projection onto the x-axis or a shadow. Remember that I can translate vectors over, so I can take this vector and I can write it over there, AY. And so now I just have a right triangle, right? And so with right triangle, all those trig functions hold, and well, the Pythagorean theorem holds, and then also the trig functions hold for that as well. The components of the vectors add to give the original vector. So yeah, so if I have my vector AX, my vector AY, if I think about adding those up, they're just going to give the original vector A, right? Just thinking about the graphical analysis of vectors and how I add them up, the components of your vectors are always going to add up in a vector sense. Now, I've been using this word add loosely. When I talk about adding vectors, as we'll see, that it's not as simple as just saying 3 plus 2, right? Like if, or 3 plus 4, for example. Like if I have this is 3 units long and this is 4 units long, I can't say that this is 7 units long, right? It would instead be what? If it was 3 and 4, this would be 5, right? Where you use the Pythagorean theorem, the square root of 3 squared plus 4 squared is equal to 5. So when I say add, what I mean is vector addition, which is different from just algebraic addition. You get a whole course on that in Calc 3. Chemists take Calc 3? You do, don't you? Chemists and Calc 3, yeah. And engineers, of course, you'll take it as well, because you have to take up through differential equations, I think. Okay, so there's our our functions. I do want to remind you and just sort of warn you that if you measure your angle from a different axis, students sometimes mess this up. Let's say that I'm measuring this angle. The x and the y components are different. So uh, here, my y component would equal to a cosine of phi, and here my x component would be a sine of phi. Now these come about from our definitions of sine and cosine. Remember our mnemonic SOHCAHTOA or whatever it is, that however you remember the trig functions. The sine of an angle, say theta in this case, is opposite over hypotenuse. So the sine of this angle is the y component over the hypotenuse, which is a. Hey, James. Uh, and then I can solve this for ay. That's going to be a sine of theta. So that's where I get this expression. But notice if I take the angle phi, then I would need to say the cosine of the angle phi is adjacent over hypotenuse, and that's going to be ay over a. And now ay is equal to a cosine of phi. All right, so I think it's okay to memorize these, and as you use them over and over, you will just come to sort of internalize that the y component is the magnitude of the vector times the sine of the angle, the x component is the magnitude of the vector times the cosine of the angle, but you always need to remember that that assumes that the angle theta is measured from the x-axis. Often what I'll do is, if I'm given the angle from the y-axis, I'll just translate it into the angle from the x-axis. So if that angle on the y-axis is 30 degrees, then I know the angle from the x-axis has to be 60 degrees. So you might want to do that as well, and that way you can just sort of, I don't want to say memorize, but you will sort of internalize that these x and y components correspond, the x being cosine, the y being sine. It's alphabetical too, right? X, y, cosine, sine, c comes before s. But you have to be careful with the angle. So if you just want to remember your trig functions, uh, that's fine. It's not going to be a big deal in Chapter 3, but it will be a big deal in Chapter 4, because we'll see, especially when we're doing inclined planes, that the angles are different, and you sort of have to be careful with how you do that. Finally, you can find the angle theta if you know the sides of the vectors, the x and y components, just from the tan function. We did that in Chapter 1 when we reviewed trig, but it's just TOA, right? Tan is opposite over adjacent, and you can solve for that angle theta. All right, that's all the trig you need to know. In some cases, you might need to rotate the coordinate system. In Chapter 4, we'll do this. It sounds like a big deal, but it's not really a big deal. Because you set your coordinate system, and usually we'll set a coordinate system just, with our x-axis laid out horizontally and our y-axis laid out vertically. But sometimes you have vectors that are not on axis, and it makes your job a lot easier when you're adding up vectors if you can get the vectors to be on axis. And if you can do that, it'll just make your math a lot easier. So for example, if I have two vectors A and B here that are laid out on in space like this coordinate system isn't very useful. I want to have a coordinate system that has axes that are on the vectors. So for example, I might draw my x-axis along the A vector. So I would make that my x-axis, and then my y-axis would be perpendicular to that x-axis. So that would be my y-axis. And then since I rotated that by theta, this new angle is going to be phi minus theta. We'll see that in Chapter 4. Don't worry about it right now, because we're not going to be rotating coordinate systems in Chapter 3. It just doesn't really come up. But in Chapter 4, it will be important. And especially, I saw a student who's in Calc 3, Daniel, I think, came to see me. He had a homework where y'all were adding up vectors, force vectors, and it very much made it easier to rotate the coordinate system. So don't be afraid to rotate that coordinate system. Like I remember as a student, I just sort of felt always compelled to draw the coordinate system like that. But you will find instances where it's a lot easier to not draw your coordinate system in that way. You choose the coordinate system. You're completely in control of that. And you can choose to make it easy or you can choose to make it more difficult. So here our angle, as I said, was phi minus theta. Let's add up some vectors. You might see a free response problem. It sort of depends how far we get. If we get how far we get into chapter 4 for the next exam. But you might see a free response problem where I just give you some vectors and ask you to add them up. You'll do this in lab as well, where you add vectors up numerically. So to add vectors, you add their components separately. So if I have a vector that's a plus b, that vector is also Rx equal to Rx plus Ry. And then the components of R are also the sum of the components A and B. So Rx is equal to Ax plus Bx, and Ry is equal to Ay plus By. Let me try to show you this. So let's say that I have a vector A. It's my vector A. And then I have a vector B right there. And adding up these vectors gives me the vector R. Now I can draw the x component of A. The x component of A here is just A. So I'm just going to say that A is equal to AX. And then I can also draw the x component of B. That's BX. Remember, that's just the projection on the y-axis. I can also draw the y component of B. That's BY. And notice now, the x component of R, which is right here, is equal to the sum AX plus BX, which is what I wrote right here. And the or the y component of R is equal to AY, which happened to be 0 in this case, plus BY, which is what we have here. This extends to more than 2 vectors. So if you have 3 vectors, 4 vectors, a billion vectors, however many vectors you have, you're just going to have AX plus BX plus CX plus DX plus however many vectors you have. So you could do this conceivably for many, many, many vectors. Let's do a quick example. Let's say that I have 2 vectors. The vector A is 1 meter long and 45 degrees from the x-axis. So my vector A looks like that. And my vector B is 2 meters long and 60 degrees from the x-axis. So it's going to be 2 meters long and at a bigger angle. That's roughly twice as far, I think. So that's B. And then my vector R is going to start here and go to there. So a couple things about that. I know when I find the sum of these 2 vectors that it's going to be at an angle that's bigger than 45 degrees, right? I want to find the direction and magnitude, and I know that this direction will be bigger than 45 degrees just from my little sketch. I always find it very helpful to sketch out the vectors before you try them. All right, so I want to know what is A plus B. Just a second, let me see. Notice here too, as I said, just to reiterate this, if I draw AX here, that's my AX. This is my AY. This is my BX. And this is my BY, my projections of those 2 vectors. Notice that those vectors add up to give the x and y components of R. So our first job will be to find all the x and y components of all the vectors. So I can find my AX is going to be 1 meter cosine of 45. AY is 1 meter sine of 45. BX is 2 meters cosine of 60. And BY is 2 meters sine of 60. see, cosine of 45 is what, 0.71, I think? Yeah, 0.71. Cosine of 60 is just a half, so this is 1, and sine of 60 is 0.86, so this is going to be 1.7. So those are our components of all our vectors. And then if I want to find the x and y components of R, I just add up the x components of A. So this is going to be 0.71 plus 1. And then Ry is going to be 0.71 plus 1.7. Which is 2.4. So now I have the magnitudes of Rx and Ry, and I just get the Pythagorean theorem to find the magnitude of R. So it's going to be the square root, and that is 3. And I can find the angle. I know this is sort of fast, but this is all stuff that we've seen before. Hopefully this is just review. Is it review for y'all? Feel comfortable with this stuff? Yes? No? Alright, to find the angle, I just do the inverse tan. Opposite over adjacent, 2.4 over 1.7, and that's equal to 55 degrees. And it's going to be from the positive x-axis. You'll always want to put in some sort of qualifier for your angle just to make sure that I understand where it's from, and I'll do the same. The default is to assume that it's from the positive x-axis. If you ever encounter a problem where it's not given, then that is the default, that it's from the positive x. But we'll see that sometimes the angle is measured from the negative x-axis, from the y-axis, or maybe below the positive x-axis. Just make sure that you're clear on that. Okay, as I said before, we're going to deal with unit vectors. In this class, we do a lot of vector notation, and it's pretty useful. It makes working with vectors a lot easier because you split everything up into their x, y, and z components. And we're just going to use the I vector to represent the x direction, the j, the y direction, and the k is the z direction. Um, so for example, if I had an r vector, let's just use the one I had before, I would represent it as 1.7i plus 2.4j. And that just says that the x component is 1.7 units long and the y component is 2.4 units long. You'll see vectors like that a lot, and on your test, of course, you'll see it in vector notation, that I, J, K notation. Here there is no k unit because it's not in the z direction. My coordinate systems, I'll let this be my I, this be my J, and then positive Z will be in that direction out of the page. Some of you might have encountered slightly different coordinate systems, but that's what I'll use. All right, let's do a few clicker questions. Guys, overall from what I heard from what I heard from students is that, you know, students that didn't do well, it's like, gosh, I didn't do well, but I felt like I understood it when I was just sort of either in class or working through the homework. Um, I think that's a common thing, and it just really takes a lot of practice to make sure that you truly master something. Lots and lots of practice. So, you know, I recommend that today you go home and you start looking at vectors. There are a few homework questions that you should be able to work. Pick one or two questions, maybe look into some of the old tests at the multiple choice and the free response. In fact, you might even want to make a little 3-ring binder and just print out all the tests for the rest of the year, or maybe print out a couple of years worth for you to practice through in the coming years, in the coming weeks rather. And then every night before you go to bed, like you can just work through a couple of little problems. Just 10 minutes before you go to bed, 20 minutes. You'll probably do that already though, right? Before you go to bed? No? Yeah, okay. All right, let's try this. If two vectors are given such that a plus b equals 0, what can you say about the magnitude and direction of the vectors a and b? Let's stop at 35. 35. Okay. Yeah, D is right. They have to be the same magnitude. Say A is 1 meter in the positive x, B is 1 meter in the negative x direction, so they add up to give you 0. The vector sum is 0. Given that A plus B equals C, that means the vector sum of A and B is equal to the vector C, and that the square root of A squared plus B squared, or excuse me, A squared plus B squared equals C squared. Here the absolute value bars say we're just going to take the magnitude of this vector. So we're just looking here at the magnitude of A squared plus the magnitude of B squared is equal to the magnitude of C squared. How are the vectors A and B oriented with respect to each other? If the vector A plus B equals C, and the magnitudes of those vectors add up, A squared plus B squared equals C squared, how are they oriented with respect to one another? All right, I'll stop at 112, 112. Very good. A is the right answer because they form the legs of a what? Right triangle. Right. So I know that the vector A plus B equals C, but I could have written it just as well. I could have said the vector A plus B is equal to C. But for the one on the right, this expression is not true, right? Because this is not a right triangle, and this A squared plus B squared equals C squared, it only holds for a right triangle. This is Pythagorean theorem, right? So the answer then is A. They're perpendicular. A and B are perpendicular to one another to make the legs of a right triangle. Given that A plus B equals C, and the sum of their magnitudes, A plus B equals C, how are A and B oriented with respect to each other? All right, I'm going to stop at 38. 38. All right, we're a little bit all over the board, but B is the right answer. Let me show you why. They have to be parallel and in the same direction. Let's say that I have a vector A. Say it's 2 units long, and then I have another vector B that's also 2 units long. The sum of these is going to be something less than 4, right? Because it's a triangle. The hypotenuse is always less than the sum of the two sides. However, if I have it such that they're parallel and in the same direction, the sum of these two vectors will equal 4. That is to say that the vector sum is equal to the vector C, and then the sum of their magnitudes is also equal to the magnitude of the vector C. That's not always true. That's only true if they're parallel and in the same direction. If each component of a vector is doubled, what happens to the angle of that vector? If each component of a vector is doubled, what happens to the angle of that vector? You might want to sketch out a little triangle of those and ask yourself, what happens if I double each side of the triangle? Well, you might know the answer right off. All right, I'm going to stop at 50. 50. All right, C is right. These are similar triangles, right? If I have two vectors that make up a triangle like this, and then if I double the length of both of those, these are called similar triangles, and the angles don't change, right? Because the ratio of the opposite and adjacent sides don't change. Uh, let's just do a couple more. I think we have time. I want to hand your test back. We'll just do this one, then I'll hand your test back. Certain vector has x and y components that are equal in magnitude. Which of the following is a possible angle for this vector? The x and the y components are the same, right, of equal magnitude. All right, let's shoot for 40 seconds. I'll stop at 40. All right, E is the right answer. If I have equal sides on my triangle, that's called an equilateral right triangle because it has equal sides. That angle is always 45 degrees. So if I think about my vector, they're both the same. This angle has to be 45 degrees. This angle, too, has to be 45 degrees. All right. We'll probably refresh a little bit of your geometry as well as your trig as we go into this stuff, but it'll come back to you soon. All right, I'm going to hand back your test. Let me tell you what you're looking at. You're going to get the form back. Now, unfortunately, the form doesn't tell you right or wrong answers. So if you want to know which answers you missed on the multiple choice, you need to go to the old exam site. And you might have to refresh your browser. I have exam 1 there. There it is. Yeah, it's coming up. Exam 1, and you can go to the end, and you can get all the multiple choice answers. All right? So you'll need to go back and figure out which multiple choice you missed. It's not marked on your test. And then to find out your grade, you'll just say 100 minus the number of multiple choice you missed times, let's see, I think they were worth 8/3 of a point times 8/3 minus the number that's written on your test. That's the number of free response points that you missed. And then some of you did get the extra credit, that little bonus, the 3 points, and I just included that in. So you'll have either at the top of your test, either a negative number or a positive number. If you have a negative number, you subtract it here. A couple of you had a positive number there, like a +1, +2, or +3. You'd have a positive number here instead. All right, let me know if you have trouble figuring out your grade, and also if there's a mistake on Moodle. I'm pretty sure there's not, but if you do think that there's a mistake, just shoot me an email and let me know. All right, you have 2 things that you're getting back, so make sure that you get both of them before you leave. You're going to get the form here, which you'll need, especially if you didn't write your answer on the actual test, and then the free response portion. So I'm going to call you up, and for this part first, come and grab it, and then hang out for a second longer, and then I'll hand back the other part, which is actually the more important part. Okay? So Ashley Sagona, Brooke Lagarde. I'm going to call y'all fast, okay? So y'all just come on up. Brooke Lagarde, Sydney, Porche, uh, Kayla, Zach Hanley, Janae, Ainsley, Zach Adamitz, Lindsay, Zane, Brandon Domingue, Stephen, Brett, Cressid, James, Brandon, Domingue, right? Oh, okay. Right, I'm sorry, Domingue. Stephen, James, Claire, Heather, Thomas, Derek,